Yeah, but
No worries.
cool.
Should I get
Um,
started?
cool. All right. I guess we'll have more people joining, but I think it's time to get started. So I'll give a very brief introduction for Dr. Junheng Li. Junheng is right now a postdoc at Caltech, in the Amber Lab, working Professor Aaron Ames. Before that, he got his PhD from USC, working with Huang. Um, and I would say Junheng is a full stack humanoids researchers, a lot of cool work on control planning, hardware implementation. And he's also a very good friend of our lab. He actually collaborated with Zhao Yuan on the humanoid survey paper, and also provide a lot of support for our Hector projects, from USC lab. So really appreciate that. Um, I guess he will talk a mixture of his PhD work and maybe his new work at Caltech. And I think the topic is very related, to a lot of research happening here in our lab. So we look forward to your presentation, Jinheng. Yes, please
Yeah.
take it over.
All right. Thank you. Thank you so much for the introduction. Let me just quickly share my screen here. Let's see. All right, give me 1 second. Okay. Can we see this well?
Yeah, yeah, works well.
Awesome. All right. Okay. Once again, thanks everyone for the warm welcome and introduction and the invitation from Professor Zhao's side. And it's good to see again some of you. I had the pleasure working again with Professor Zhao and Zhao Yuan on a few of the projects here, and it was my great pleasure again to be invited back to give this talk, kind of summarizing some of the work I've done during my PhD and during the postdoc I've been doing here at the Caltech. So the today's talk would be towards model-guided learning on humanoid robots, and let's get started. As many of you may already know, there are a wide variety of motivations studying humanoid robots, right? For example, I think one of the driving factors many people claim right now is the severe labor shortage coming into the 2020s, associated with increasing fidelity rates across many industries. And in this phenomena is also like worsened by fact of the aging populations, especially in the U.S., inflations, increasing worker compensations, and all of that. So you can see all the scary charts and numbers here. So it's driving the industry to consider more of these automated options, such as humanoid robots in general, right? And many people now call it the day or the age of humanoids, and not only just because of the hype, but also think the hardware and embodied intelligence is converging to a certain point where humanoid may just make sense, and it's always has been like the final fantasy for human beings, right, to create autonomous robots that's similar shaped and can do similar stuffs that we do. But I don't believe the technology is really here yet. I still think humanoid has in general has a long way to go in both the research arena and also like exploring the true market where it belongs, right? So I think I will skip some of these motivations and the long, videos of these fancy humanoid stuffs. I believe you guys here have watched them a couple of times, right? So the current stage of challenges I believe we face in humanoid robotic intelligence in general, right? We see from the big companies and research institutes, it is converging to a point where each entity is pursuing their own humanoid like foundation models or for general behaviors or for decision makings for just low level controls, right? And upon examinations, we can see these structures are sharing similar stuff here, right? So they're all trained up these models based on some human interventions, either from teleoperations, either or from like human in the loop control. Um, and if we took like the research arena as well, some of these research works recently also exhibit similar trends or the behaviors, right? Particularly in the motion tracking and learning side, where humanoid is learning human motions, which is funny because years ago human dances like robots, now robot dances like humans, right? Now we see this field is converging heavily into the demonstration of human needing the human data collection. Though very promising as of now, I think it poses still some potential challenges down the road that we may not see right away. I hope this does not really upset any of you because I think many of you comes from the similar background as I am, and hopefully this is safe to talk this here. Um, and this is a famous example of the Tesla bot foundation model that is similar to the FSD kind of learning pipeline. And on the flip side, right, we have the FSD actually trained based on 10 years or 10 years more of driving data collection over 30 petabytes of a real world recording of these video data of human expert driving, right? Now, if we scale this to humanoid robots, it becomes very difficult because there's no deployment of humanoid yet, and hence no real world working data from the factories, right? Conversely, humanoids needs good foundation models or need these good controllers to be able to perform tasks autonomously. So it becomes kind of like a chicken and egg problem, as you may know. And we now force us to use these video demonstrations or retargeting or even teleoperations to get these high quality data with interventions of human in the loop, right? And in many cases, they are very expensive and they, are resource constraints and also inefficient. In most cases, when there's like human interventions, there's prone to errors, right? This is a famous example. I don't know if you see this or not. This is just Tesla bot casually taking out their VR glasses during middle of work. So we want to, stay away from that and try to be more constrained in terms of what we are feeding into the robot, right? And another kind of like counter example I can give is human demonstrations will only work on humanoid robots. If we discover any new form of robotic system, it might be difficult because we don't share the same morphology, right?
Hey, Junheng,
Um,
I think this is an
yes,
interesting video. I heard people criticize this Tesla bot is teleoperated. It have this
yeah,
motion like seems
yeah,
the teleoperator take off the headset from the head. Do you
yeah.
believe so, or you think it's truly?
I think it can be two ways, right? But either way, so the first way would be, they're just teleoperating and the teleoperator is not really experienced. And the other way is just they collected data or they didn't trim their data during the data collection and train the model with, all of this. So either way, that shows that it's still error prone and it's not robust yet, right?
Yeah.
Okay. So given these sort of motivations and challenges with current state of the art of humanoid robot, and going back to the topic of model guided learning, I will now first kind of introduce this evolution of humanoid robots and how the control and planning side uses different kind of method for leading all the way towards the learning driven methods right now. If we take a look, the evolution of motion control techniques of humanoids, starting from the classic models like LIP, ZMP, through some more explicit method like HCD and more intricate formal modeling strategies like the inverse dynamics, operational space control, and then to the more recent optimization-based control strategies like whole body control, or variants of MPC or hierarchical optimizations, we see a nice kind of steady progress along the way, and each method is somewhat built upon the previous method, right? So it's kind of nice because everything is connected and stuff until we hit learning arena, right? We see, namely these motion tracking RL, end-to-end RL. That is, we see there's a little bit of a disconnection from the previous method that we already know, right? And one may argue that policy optimization is just kind of like a different scale of numerical optimization, but still it uses, method that is somewhat new to at least the control side of the people, right? Um, so we have seen some tries of combining these two kind of arenas together, right? Motion, like namely, I think one of the hot topic is learning augmented NPC, and I believe the latter group is also, experiencing some of these right now, and I have seen some works from this. And my goal here is actually try to combine these big circles here with all the knowledge that we already know, or at least starting from something simple, and use that as the guide to the learning, and what we call the model guided learning framework. Yeah, so that's kind of like the big picture and how we want to approach this, right? Not completely leveraging learning, but using some like physics and model guidance in the learning process. Okay. Right. So in this conception, at least, we aim to build a ground that leverages both optimization or model-based intrinsics, and at the same time policy learning in humanoid control, and to embed strong physics and model-based intuitions to produce more robust and adaptive behaviors or more generalizable behaviors. And the bottom line is with minimal to non-human data dependency in this case. Okay, so I'll give a quick overview of today's talk. I will cover three major parts, and all the work pretty much I've done from my PhD to current pursuit, building towards what I call the model guided learning, right? So the first section will be on just some quick recap of pure model-based hierarchical optimizations that I've been working on during my PhD. And the second section will be my first tries to integrate learning aspects into optimizations, namely using these supervised learning in MPC. And the last section will be leveraging these analytical model-based method during the training of RLs and to robustify and to diversify the motions and capabilities of humanoids. Okay, so the first section specifically will focusing more on the MPCs and reduced order modelings and how they fit in the whole humanoid control, right? Well, this is sort of like a known knowledge probably for you. It's just some preliminaries around like modeling choices for humanoid robot dynamics. I believe many of you already see these figures from Zhao Yuan's survey that we co-authored. So at the highest level of fidelity, the whole body control, right, captures pretty much everything: joint states, actuators, external forces, or any of these joint actuations, right? And on the other side, we have centroidal dynamics, which is a good representation of the whole body. But at the same time, it represents, all the limb inertias and stuff into the COM space, and does not really care about the limb dynamics per se. And you can further augment this with the kinodynamics models with joint space informations in and at the end of this spectrum, we have the single rigid body dynamics, which you'll hear a lot in this talk, at least this part of the talk, where I use, and I call it the potato model, right? And you can see from the right-hand side of the spectrum to the left, we have a increasing computation effort. As a trade-off, we have more model fidelity to represent the actual system, right? And then the balance between the two is where I want to, fit my work in and try to seek the balance between the two to achieve more dynamics, but at the same time computationally friendly with onboard unlimited resources of computations, right? Okay. So the first try we did is mostly just on the hierarchical optimization side, right? So we leverage some of these nice structures of the hierarchies with optimizations with NPCs. I believe this is kind of like straightforward for you guys. So I won't go too deep in this, right? So the first high level and mid level, we have the trajectory optimizations or the MPC to take care of these high level planning and some of these motion generations and control action generations. And on the low level, they're more like a joint level control, like whole body control and stuff. And my primary focus is more on the high to mid level where I do the planning and decision making, and then for some level of control there. Okay. So the first try dating back to 2021, our investigation focuses on a very simple model, the single rigid body model strategy into the MPC. So we simplify the whole layer structure into heuristic-based contact planner and just single rigid body MPC as a main control level, kind of like using fixed periodic gates to do locomotion, right? So the investigation focusing on using a simplified model, namely this potato model, a single rigid body, and we choose this model to have these 5D reaction forces and moments into these dynamics modelings, right? And so it's very simple, and with some assumptions and simplifications, we can fully linearize and make it a convex MPC formulation. So I won't go too much math detail here because I think this is kind of trivial to you guys. So with that, we can do already pretty nice balancing or locomotions, or these nice turning and won't get dizzy or these turns, and even uneven terrain locomotions, right? So this is just a baseline of what we can do. But then I found out this, right? So if you push the robot, because it's a fixed frequency walking, it will definitely fail because it just does not adapt its foot placements really well because we don't really leverage the higher layers of control to plan for any of the foot steppings, right? So the next natural step is kind of like also leverage this high level here, having multiple layers of optimizations to achieve different dynamic motions. Now, if we modify this and have this nonlinear MPC sitting on top of the high level layer, we can formulate different kind of like tasks modulate kind of different behaviors of the robot. Like for example, we can do terrain, and we're planning on the high level to do like stepping stone traversal and do trajectory optimization online to do these nice jumps, or do push recovery predictions for these robust locomotion behaviors, right? So to give you some examples of what the actual implementation look like, right? We have this nice stepping stone traversal in simulation that can do this really nicely. And we also have some of these jumping online planning and a balancing control for the jumps. Okay, the robot doesn't really know that there is a perturbation to the terrain. And again, the robot is jumping down from the 20 centimeter block that does not really know that the block is there. And also doing some of these autonomous planning and jumping over boxes. Okay. And lastly, we have these nice push recovery behaviors that kind of adapts its stepping strategies right here. Right. So you can just kick the robot; it will be able to balance based on the kick and prediction of the COM. And adapts its foot placement and stepping strategies. Okay. So furthermore, if we want to extend this idea to local manipulation, especially the case where robots need to handle kind of heavy payloads or move a sizable object, we can, modify our reduced order modeling approach to include both the object dynamics and the robot dynamics, and then simplify them into linear forms that can, again, throw into a convex MPC formulation to inform the controller that has certain masses that need to manipulate, right? So this is an example of the robot carrying a ball first and then throwing it while doing locomotion and balancing all together. Okay, so this with the rich information of that contact sequence that inform the MPC. Okay, and also we can do some nice perturbation resistance behaviors in push recovery or in push manipulation. Right, the robot will stay on track even with the push. And just a few more hardware experimentations doing local manipulation, carrying like different payloads, right? So maybe one day the robot will be able to carry the groceries for you, um, and going over like rough uneven terrain while carrying the payload. Okay. So with this, the main takeaways for at least the first section or the majority of my PhD work uh, is that reduced order models are very strong, right? Hierarchies are kind of necessaries for different kind of tasks. But again, there comes to the drawbacks of the generalization because you need each task to have certain amount of manual input to your controller or to your planning level. So it's not really autonomous or it's not really generalizable to different kind of tasks that I want to do, right? And plus, there's the natural gain tuning and controller brittleness to the model-based strategies. So in short, there's just so much of effort in deployment, right? You have to do the tuning for deployment. You have to do all the low-level stuffs, sensor fusions, and state estimations, all of that, which just becomes very daunting in practice. And that kind of like motivates me to do the next section of the work, where we try to leverage some of these learning methods, namely the supervised learning, to augment MPC and to represent some of these unintuitive aspects that we cannot really represent with this pure model-based method, right? And this naturally leads to an ongoing discussion between model-based and optimization-based and a learning-based method, and how they, compare to each other. Right? I like to borrow a sort of like a memorable analogy from Professor Sam McCabe's talk, where he compares model-based optimization to a well-trained obedient butler. One can really follow your every dynamic model or constraints that you give. And on the other side, you have a learning, which is a wild beast that is really powerful, very strong, and can do like these diversified motions, but it's very unintuitive or like hard to control, right? Even though it can do like all of these nice end-to-end pipelines with, diversified, the domain randomization and to enhance robustness during deployment. Again, there's a lot of intuitions that we cannot really just grasp compared to like pure model-based approaches, right? Okay, so if we can allow the butler to control the beast or tame it and do whatever we tell it to do, that would be the ideal case. And this part of the work is here my first try to sort of like taming the beast or leveraging the idea or leveraging the power of the beast with the butler, right? Right. So here I call it using learning to improve control. Okay. So the first section I want to talk about in this part is how do we infuse these contact implicit behaviors in reduced order model based locomotion and PC, and we see these nice, very nice videos of contact implicit NPCs and plannings, and the background is also kind of like resource constraint because a lot of these methods requires high fidelity whole body models and require like simulation level of fidelity to be able to simulate and also do the contact implicit planning, which becomes very daunting and very challenging. So what I want to do is I want to leverage some of these learning aspects into MPC, but you still uses a reduced order modeling that kind of like fits within my research arena and do these kind of like contact implicit planning or decision making in local motion, right? So what we want to propose here is called the GateNet augmented MPC, where we try to infuse a learned policy into the numerical optimizations solving mechanism level and seeking a deeper integration between the two, right? So now on the framework scale, we still retain a hierarchical optimization fashion, but within the MPC, the hierarchies becomes kind of iterative. We try to leverage this MPC to solve for the step locations, durations, and contact forces all at once. So in like practical walking cases, it will still be a periodic walking, but it can reason about these stride length, stride timings, and all of that, right? And the overall idea is we want to leverage what we know about like the whole body dynamics model and with the high fidelity, right? But with the centroidal dynamics model is becomes like easier to represent or to compute online, but it doesn't really have the nice coupling of the step duration or the step location kind of like behavior because it simplifies all the leg dynamics into or project them into the COM space, right? So what we want to do is we leverage this whole body dynamics where it does represent the two-step dynamics really well because it has all of that limb inertias and limb actuations that is in the effect of the dynamics model. With this, we can construct a whole body MPC with variable step duration, throw this into my simulation and collect a bunch of different scales of data to relate state information to step durations. And this way, we don't need to actually solve this very heavy whole body MPC during the deployment. Instead, we learn what we call like a gate network to capture this very abstract decision-making process between the stride duration and the current dynamics of the robot, current states of the robot, right? So then that network will predict a DT for the MPC that will be interpreted into the step duration of the centroidal dynamics model. And hence we only have these bilinear constraints of the full location and the forces that we can just use a pretty standard sequential QP solver that we can throw in our simplified MPC subproblem and the GitNet and also the spatial momentum updates. Okay, so we first do the linearized QPs at each iteration, and then with that local solutions, we update the DT MPC for the via the GitNet, and then update the centroidal pulse and momentum reference trajectories based on the local solutions of DT. Okay, and then we solve this until it converges for each step. All right, so with this, we can already do very nice walking behaviors on these stepping stones because we can now explicitly constrain the foot landing locations in this MPC. Okay, and this here are just a few different videos of doing, push recovery and different locomotions on uneven terrains and even with virtual gaps, and even extending this to local manipulation with unknown load that will be able to adapt. Okay. However, even though we see some of these nice videos of the GateNet MPC, there's still many behind the scenes efforts, especially on the gain tuning side, because now we have multiple, controllers to tune, and also the large scale of a large dimensional space of parameters. Right, so all of that you see is just behind the scene that we have to manually kind of tune, which is unintuitive for most people, and it becomes like a actual task we have to do every time we go into like essentially like a new terrain or a new behavior, right? So this kind of like motivates me to do some of this recent work that I'm doing here at Caltech, is we want to really leverage leverage learning to kind of like help these model-based intrinsics, right? One of the work that we did recently is learn to tune the control parameters, right? Is how to formally investigate the control effect or the tuning effect of each model-based controller, right? So previously, the current method, such as the Bayesian optimizations, you may already know, struggles with scalability as the dimensionality of the parameter space increases in the gain tuning, right? So a good example here is in this bipedal robot here, they have to really reduce that dimensional space from 54 to 6 for possible deployment on hardware. So what we introduced was we call the auto tuning framework, leveraging the diff tune that the folks at UC developed, and it leverages the first order information of the optimization and the controllers and to solve for more of an efficient MPC parameter tuning and learning at the same time. We actually were able to do this with a parameter space of 240 comparing to these Bayesian optimizations where they have to really constrain their parameter space in tuning. Okay, so a simplified kind of like system diagram is this. We use our standard locomotion MPC and simulators. That a key challenge kind of is the selection of appropriate robot dynamics here, because we want to really represent the the kind of like the whole spectrum of the dynamics, specifically the contact forces and moments of the robot walking. But with the single rigid body model, as you know, the actual dynamics is really kind of far away from in the single rigid body, right? So what we have to do is kind of like find a balance between the two. The option one obviously is single rigid body, and option two is leveraging the full order model, but is somewhat difficult to differentiate, and also it prolongs the learning process for the auto tuning. So what we want to propose is a ground reaction force and moment network that really leverages the MPC ground reaction force and moment commands alongside with the ground truth ground reaction force and moment data that we collected from the simulation. And this network basically captures the discrepancies between the command from MPC and the actual ground reaction force and moment feedback from the simulator, and learns the kind of like the mapping between the two, right? And this way we can enhance the single rigid body model fidelity. At the same time, it won't add too much of a computation overhead for the auto tuning or learning process. Okay. So with that, we can actually learn any given trajectories with this associated optimal control weight. This is a kind of like a zero-shot deployment here, where we learn this optimal control parameters for this S-shaped, following an S-shaped curve, right? And as you can see, compared to this nominal method or untuned method, we can have around like 40% of tracking loss reduction here. All right. And these learning parameters are also very surprisingly robust to deployment uncertainties, right? Allowing the robot to traverse different terrain types and also even with added mass to the robot, right? So we train this parameter with just a biped, and now we extend this to a humanoid without the knowledge of the added mass to the parameter space. Now with this trias, you can probably see, right? The robot is able to follow the desired path and also traverse this nice stepping stone terrains, or not stepping stone, uneven terrains, where the nominal controllers with the nominal gains will not be able to do that, right? So this is pretty much the end of this section. We never really got away, as you can see, from the disadvantages of model-based controllers, right? So all of that low-level stuffs and game tuning we still have to take care of. Even with this nice auto-tuning framework, we see for each like trajectories we have to have a separate parameter or a setup of parameter, which just becomes very challenging or time consuming for generalization, right? So this kind of motivates the next tries of
So
combining actually model.
Junheng,
Yes,
can I have one quick question? Can you talk about what are these parameters? Are they the controller PD
yeah.
gains? Or I saw in the diagram you have this theta. parameter. Can
Yeah.
you talk a little bit more? What are they?
Yeah. So this can be any parameters actually you want to represent in the controller space, right? So anything that you can differentiate and get first order information. So here we only do like all the control weights in the MPC where we formulate the cost function. So namely the tracking weights for the trajectories and these minimization weights for the ground reaction force and moments, and also some of these parameters that we can tune, for example, the mass of the robot. Um, so it really depends on how you set up your model and how you set up um, your trajectories, and it will be able to kind of like learn different spectrums of parameters. But honestly, there's upon our sort of like investigations, certain tasks or certain trajectories only is correlated to a certain amount of the parameters space. So it doesn't really need to tune all of that parameters for at the actual deployment. But we just show here that we tune all of that parameters just to it is possible to have this high dimensional space of parameters that we can tune with this framework. It's scalable, right?
Mhm. So in case if you tune some of the physical parameters or kinematics parameters like the mass, as you said, is that this problem is sort of like a system identification problem, like you are trying to learn the
Yeah.
sort of the the best parameter maybe matching to the reality, I guess.
Yes,
Is
so we actually had a follow-up paper on this that is called Deep Co-Tune. That is a co-tuning between the simulator and the actual controller. So essentially doing system ID and gain tuning at the same time to kind of like match the two for better sim to real, I guess.
okay,
Yeah.
cool. Yep.
Another quick question. Here you're trying to tune the parameters in the simulator, right? So if you want to go on hardware, that is still having some like sim to real gap, right?
Yeah.
Would this auto tune solve that part of the problem?
With this deep tune framework, I think is still a bit challenging because right now you see we have Hector here, right? So it's a very rigid body like robot, and and we use a single rigid body model to kind of like address this simulator dynamics here, right? Which kind of like works for us, at least on this robot. But I would assume you without much of effort, if you want to do this on like a G1, for example, it could be challenging because the dynamics model just don't really match well, right? You have to do more of this system ID or the code tuning process. But in our like diff code tune framework, it actually will be able to address all of the uncertainties in like simulators if you have like parameter physical parameters that you want to tune that will be able to match the actual hardware well because the code tuning process doesn't need to be relying on simulator itself. It can also be a real world rollout from the experiment, right?
Yeah, that sounds great. Thanks.
I have another question. So,
Yeah.
so in this paper, the objective function L is the difference between the NPC's predicted ground reaction range and the actual like simulation ground truth range, right? So if you wanna like apply this work to the rollout in from the actual hardware experiments, so if you replace this objective function with let's say the tracking error. Do you think
Mhm.
these methods can be applied to like real world rollout? Um,
Yeah, so I believe we didn't do any we didn't do any real world rollouts for this particular work here, but I think the folks at UIC they leverage this framework to do more of the different kind of like robotic system, like the manipulators or drones, and they were able to do it on I think real world rollouts pretty well. And it really depends on what kind of like dynamic models you give to in this simulator part, right? It's difficult in the sense that for bipedal robot, if you want to do like the whole body dynamics, it is high dimensional space, and difficult to diff tune is going to be really slow or hard to differentiate this dynamics model. But if we do like real world rollout, we can actually get the first order information already. So it's actually something that we wanted to try, but just didn't have the time to do so.
Okay, thank you.
Okay. All right. So I think this is a good point where I go into the more of the claimed stuffs, or the one that fits my title of the talk, where is we try to leverage the model-based intuitions into the modern reinforcement learning pipelines and do all of this model-guided learning, where we seek analytical models guidance in training loops and try to leverage RL as a pretty much a compiler to package everything all together, right? Okay. So this way, instead of using learning to improve control, we want to promote the idea of using control to improve learning here. Okay, so this is like pretty much what we claim in Amber Lab, and we try to like really promote this idea here. And as experience, right, the RL is a very, very powerful tool, and we can do a lot of things with it. It's hard to interpret it sometimes, and we can give it some explicit guidance to it, right? Okay. So I want to first kind of like introduce this model-free motion tracking RL that a lot of people are doing nowadays, right? There are very established literatures and pipelines on this motion tracking RL kind of concept that pretty much leverages like human expert demonstrations with mocap data or mocap cameras, and then we can retarget this data frame by frame using optimization-based method to the humanoid action space, right? And then throw this nice trajectories into the RL training loops, and then you get like a nice policy that can do the backflips and do the dancings and stuff. So you can see all the heavy liftings is done offline, where you have to collect the data and do the retargeting, which are all just single motion, right? For each motion, right? So you can see this is very difficult to do it in the loop, or the process in the loop, because it requires like some human interventions, and also the retargetings and all the data collections is really really difficult. Otherwise, you're stuck with distillations if you want to like train up different policies and just combine them together. But there's always like averaging effects between or after the distillation, right? So what we want to promote here is we want to really leverage the model of the robot that we all know, both the kinematic and dynamic ones, and use the analytical derivations of those, and we can generate these motions ourselves without the need of human demonstrations, or with very minimal input of the human demonstrations, right? Essentially, if we could generate these analytical full body motion trajectories online during the RL training, it will be possible to infuse this process within the loops and let the robot learn kind of different kind of behaviors, as long as we can provide these intuitions of what motions we want to generate during the training, right? So that's how I kind of define the model-guided RL in our scope. And the first work we did recently is introducing a stepping stone local motion framework, or stepping stone planner, based on the well-known multi-domain lip dynamics in walking pattern generation, right? Where it just kind of serves as a physics-based ROM synthesis for each like step of the robot, okay? So with that, we can generate the COM and foot placement trajectories that is dynamically consistent with the robot dynamics, robot reduced order dynamics, and also environmentally consistent with whatever the environment is you set up in the RL training, right? So with that, we can establish a three-stage teacher-student policy training framework. And note here, instead of relying on much of the nominal reward shaping that a lot of people are doing in the reward engineering, right? We leverage what is called the CLF-based reward, and it's also kind of like a nice contribution of Amber Lab here that we did previously, where the CLF principle is basically a well-established idea that we can design a control layout function based on the control goal here, which is ETA here. We're just, in this case, motion tracking of the COM trajectories or motion tracking of the foot placement, right? And then we can find a proper layout function based on that um, uh, control goal. And then skipping many steps here, the CLF will allow a guaranteed exponential convergence to stability. Like when you place a beam on the inside of a bowl, it will always drop to the bottom. So that's the guarantee of the stability for the reward convergence. Okay. So with that, and with the whole framework, comparing to like the regular end-to-end policies, for example, like the Beam Dojo or the AME frameworks that all does the stepping stone locomotions, right? Where the walking is kind of like constrained into period 2 walking style, right? So it's stride twice on each stone, versus our method. With this strong guidance, we can do period 1 walking. That's more efficient than agile in practice, right? And this is another example of a long stepping stone course that we did. That's kind of like shows the capability of the robots in generalization, right? And we increase the difficulty of the course, right, from just the width difference to height difference, and also to the narrowness of the stone, right? And towards the end, we have pretty much all of the auto distribution terrain shapes that the robot just learns by itself. Okay. And on the hardware side, we're able to kind of transfer it very nicely with this walking. And this is just, you can see with the robot stepping on each stepping stone very nicely and very precisely. And the second video here shows, sparse foothold, right? The robot really stretches leg to cover that stone, that gap. And this is a really cool video. We recorded it with a front mount camera, just kind of seeing the terrain. And even with the narrow the stones, right? You can also have the robot traverse it, and the robot just intelligently decide it can skip one stone to be more efficient because the momentum is building up and it won't be able to slow down at that point, right? Okay, so this is really nice, kind of like a try that we did with model guided RL. And how do we extend this to more intricate whole body control, right? With this success, we want to leverage, this model guidance of the whole body. It's essentially whole full joint space of a control that with some explicit model guidance. So give you a background of the challenges of current whole body control schemes, right? So optimization based obviously is really nice in terms of like constraint handling, and you can input any sort of like dynamics onto it, right? But again, there's exists excessive parameter tuning and also higher heavy layered architecture that we need to build upon this in terms of like planning side and also the state estimation, sensor fusions, all of that, right? But on the model-free RL based side, we have this exponential, the exceptional behavior with just expert motion tracking, right? So these expert RL policies that can do these wall flips, dancing really well. But again, it's a low sample efficiency. We only learn one policy or one motion per policy, and generalization is still kind of questioning with all of that, right? So again, going back to the idea of model-guided learning, we want to leverage this model-guided or model-based method or intuitions into this model-free RL and try to address these downside with what we know in model-based the world, right? So with this attempt, the generalization of full body references for our RL, normally this process is done with these steps, right? We normally just reduce the complexity of the whole body model to some reduced order model, and which really considers just the reduced order or the single rigid body COM and end effector locations. And based on these key end effector locations, we can then use inverse kinematics to generate like full order joint space motion references, right? And unfortunately, this process is an optimization problem because we're mapping fewer variables in the Cartesian space to a higher dimensional space of a full joint space, right? But the overall goal is how we can wrap this whole process into the RL loop. So we can explore different kind of like walking behaviors and whole body behaviors autonomously, right? And as we know, from the model-based background, this unconstrained optimization problem for the inverse kinematics at each frame is essentially possible to be reduced to a closed form solution by a first order optimality condition, right? With this convex optimization problem, right? So if we do that, and we only need like actual just a closed form solution to solve within the loops, right? To give you a kind of like a scale of the performance difference in computation time, just with this simple method, right? To generate a trajectory of 2 seconds long with 50 frames in the training loop, with the parallel as a OSQP solver we set up, it takes about like 10 seconds for each parallel evaluations for all 4096 environments. And with a closed form solution, we can just code up really nicely in PyTorch. That will reduce that to only 1.5 seconds for all of that 4000 evaluations at each update, making it somewhat real-time feasible for the RL training. And with that, we did some simple sort of like demonstrations how this works. With local motion, you can see this is on the left is an example of motion guidance generated with this closed form solutions in the training loops. And then the right side is the deployment of that guidance in hardware. Okay. And we can, once we did some of these more whole body kind of like demonstrations within the RL loop, and just based on like a random like contact points and effector locations, and we generated like different kind of motions based on that. There's no human input. We can do this whole body control in terms of like walking and even crouch walking with some like squatting there. And also like just doing tele operations with our own like whole body controller, and we'll be able to stay in balance with pretty abstract motions, right? And I think towards back here we have, let's see, yeah, like even squatting and doing some of these pretty fast hand movements here, right? Okay, so I think this work is still like ongoing, and we try to hopefully publish to or like submit to IROS. With that, I think we can do more of these actual applications with extending this to local manipulation and to some of these lab works that we want to do that is more tailored towards like different specific applications, right? Right. So I think that's pretty much it for the amount of work that I want to share. But just lastly, I have some other cool stuffs that we have been working on at the lab with the industry level of a support, right? So this is just having the robot carry a drone and take off from its back Oops. Let's see if this works. Yeah, so this is taking off from the back of the robot. So the bending over and bending up is easy, right? This is all control. The hard part is how to do this autonomously because essentially this will be a multimodal planning problem because now we have the robot, we have the drone, and we have different capabilities of walking and flying. And then we have the combination of the two and the discrete decision making of detach and attach. So it becomes like a huge planning problem that we want to. So the goal is that we want to do this autonomously and having this planning layer on top of it just to do like some nice actually applications in the wild, right? And this is another example that we mentioned previously, that Westwood Robotics Themis robot that we just mounted a huge drone on the back of it. It will be able to do the locomotion nicely. And again, the goal is to have the robot take off the drone and then do like have the drone do the navigations and have the robot follow the paths that the drone that generates, right? So a kind of like an ambitious goal that we want to do for the next demo that we're gonna face in somewhere later this year. Okay, so with that said, I think that's pretty much it for the talk, and just some acknowledgments to all the collaborators and partners and funding sources. And yeah, thank you for listening, and I'll open to any questions.
All right, thanks, Junheng. Very excellent talk. We have time for questions. Maybe I'll start with one.
Yeah.
So is this, I think this for this whole body control work you present at the end, are you trying to incorporate some of the CLF components, in this work as well, or they are separate?
Yeah, I think the goal is to have CLF in pretty much all of the control frameworks or the RL loops that we have is what we try to kind of promote at these days. Yeah.
Okay. And I'm actually curious, even when you use the reduced order model, like this stair climbing paper,
Yeah.
how much do you mention this CLF actually help to provide some strict, constraint or guarantees? But my
Mhm.
understanding is you put this CLF, this energy function reward as a reward in the RL setup, right? So the whole
Yeah.
framework is kind of like RL setup, and you are trying to kind of push this energy point to the minimal as much as you can. But
Yeah.
it's overall it's still like a RL reward. So I
Yeah.
wonder.
So it's still in the reward design. Yes. Correct.
Okay. So I'm just curious when you say it provides the stronger, formal guarantees, in what kind of sense it is, or it's still rely on this reward, you are trying to minimize the reward at the end of the day, in the RL setup.
Yeah,
Does
I
the
think
question?
the overall
Yeah.
goal, yeah, still to have this in the reward, but we can formulate some sort of guarantee of this with some arbitrary selection of parameters here in the P function here. We can still be able
Hmm.
to guarantee a convergence or have similar behaviors of a well-engineered reward function. Yeah.
Hmm. Hmm.
Yeah, so
Yeah.
essentially having more, I guess, autonomy in the exploration of the reward, and also be able to alleviate some of these reward engineering or parameter selections for rewards. Right?
Hmm. Hmm. Okay. Okay. And how this reduced order model is incorporated in this framework? I didn't guess like the leap
Yeah,
model, right?
this LIP model, right?
Right.
So
Yeah.
this is actually Min's previous work that she did in the Cassie robot. It was basically a reduced order synthesis of multi-domain walking behaviors with the LIP model. So essentially, all we're generating is the COM trajectory and footstep locations, because now you can specifically constrain the foot location to be somewhere on the stone for each stride. So this way we can produce, based on the synthesis, we can do pretty much dynamically consistent walking based on the analysis, and then it's all the good thing is it's all analytical and closed form. We can just solve it online, and it's not much of a computational overhead. So in the training loop, we can use this guidance to guide some of these motion tracking primitives. Yeah.
So and then it's later kind of encoded into this CLF based reward function. This reduce
Yeah.
order
So all the
motion.
generated motions or motion guidance will
Okay.
be
Okay.
in
I
the
see.
CLF. Yeah.
Okay.
Yeah.
I see.
Mhm.
Okay, cool. All right. Other questions?
I have a question. So, about the analytical solution for the QP,
Yeah.
could you go to that slide?
Yes.
Yeah, so I didn't really understand how this idea is related to like your model guided learning approach.
Oh, okay. Yeah, so I think I didn't really explain this part well. So essentially, if we want to put this unconstrained optimization problem that will give you a specific, like full order joint space guidance into the RL training loop, it's somewhat computationally heavy because it involves solving a QP problem parallelly. But if we can solve this in a closed form and just have a somewhat a closed form solution that is easier to compute and do parallelizations, this will give you a faster training, and it will be able to explore different kind of motions more in a shorter amount of time that the policy or the policy optimization runs, right? So the bottom line is we want to generate motions or full order motions in the joint space with first just the inverse kinematics with some reduced order model guidance. And this is kind of like a necessary step that we need to do to map all of that reduced order model locations into joint space, right?
Okay.
So as you can see here, this nice walking behavior, this is all generated based just on some key COM locations and contact locations, and then we do inverse kinematic mapping at each frame in the RL training loop that is really fast. So all of that generates within like 1 second of amount of time, right? So this will be for all like 4,000 environment updates, right? So it's fast enough to do it in the loop, and it's also give you some nice motions already, which is powerful for all of that motion priors, right?
Okay, so this motion prior, so I guess you first then generate the motion using reduced order model, and then like map the key point. So you can use inverse kinematic to find joint space reference from this reduced order model
Mm-hmm.
reference, right? So during the RO training, you still generate this reduced order model reference online, or like, is it just an offline generation and then
No, this will be in the loop.
in the loop? Okay.
Yeah.
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 Okay.
So you can base on, for example, if I would just want to do like walking behaviors or learning different walking behaviors, I can generate these uh, these COM or rigid body based models in terms of just COM velocity and foot stride length. And with these commands, you can randomize those and generate different walking motions based on those key kind of determined factors, right? So you have a different wide variety of walking data that you generate online that can guide the RL to do like different kind of walking behaviors.
Okay. I have another question. So I think this part, like this model guided learning, it's basically incorporating model based knowledge into RO training, right?
Yeah.
In the area, right, in the first stage, first part of your talk, it's more like incorporating the running into the model based methods. So I just wanted to ask, like, which do you think is the most like more promising approach these days? Because I also thought about this in the
Yeah.
past and want to know
Yeah.
your opinion.
That is a very good question, and I have been like trying to explore and trying to understand, which one works better or which, what are these weaknesses and strengths, right? Um, Honestly, I think nowadays, with all of that nice pipelines in RL and good things we see in RL, it kind of like shows promise that it's nice to be a good bottom layer that can wraps everything around. So as I mentioned before, or this is coming from one of my lab mates, saying that RL is a good compiler that can pretty much wrap everything together for your policy and for your control and give you the ease of doing like deployment, right? So with model-based kind of like foundation, like you have the model-based method sitting at the bottom layer, you still have to do all of that stuffs with, like I mentioned many times, with state estimations, with the sensors, and with low-level mappings, and obviously, model-based has the gain tuning issues as well, right? So it's just a lot of work. I think many people want to kind of avoid doing. And honestly, given that I have tried both method or both directions, I think the RL way is, or the model guided RL way is kind of like more straightforward to me in terms like how do we like deployment aspect, but the learning augmented MPC way is what I like and what I think it will be a good kind of like direction that it will never really die because the MPC is really strong tool. It's just like we haven't really fully explored it yet, right? And with some of these effort now, like sampling based MPC that are using like large scale simulations, I think it still have its values and still has its advantages in many ways. So I can't give you like a definite answer which one is the best, right? But I think it just depends on what your task and how do you want to do the whole pipelines, right? As RL is just very popular and easy now to implement, right?
Thanks, Aaron.
Yeah, I think this is a great conversation. We have been working on this, model guided RL, the Opto-scale paper. I think Fukang has,
Yeah.
published before. But one thing is, all the data set has to be generated offline. And we are using trajectory optimization, and we actually think about how to make kind of the this trajectory generation as an online process, as an MPC planner. But I think it's still we are using Crocodile, which has some a limitation. I think they are pushing for the online MPC version for that TO setup. So we might give a shot on that front. But my understanding is your
Right.
framework is kind of online. Is that right? Like the high, you are kind of
Yes.
like the stairs is doing some kind of like online planning for the foot placements
Yes.
when try
Everything
to
is
figure
online.
out.
All the planning trajectory optimize generations are online. Yes.
Okay, so I think this is kind of leveraging the benefits of reduced order model. But for the whole body control, are you planning to maintain the same setup, like do the whole online setup for this?
Yes.
Okay.
Yeah. So
But
currently this
Mhm.
is also online, right? So everything we generated is online, and all the inverse kinematics are done online. The reason we cannot really do MPC or like dynamics based yet is just a pure kind of like computation burden
Yeah,
with
I think we are facing the
full
same
order
problem.
models, right?
You are kind of
Yeah.
using here you are using reduced order model, and then IK generate the full body, data sets.
Yeah.
Which is okay. I see. Cool. Yeah, this is I think we have a very similar problem, a similar setup. Maybe well, Fukan didn't speak much today, but I think you guys maybe can have more conversations, and there
Yeah.
maybe something we
Of
can
course.
work together. I feel this is a very relevant problem.
Yeah.
Um, yeah, and we have some other work like using, diffusion at a higher level, sort of serving as the MPC planner and incorporates
Uh-huh.
more visual inputs. I guess here you are not using any, perception components for the stare detection, right? Um,
So
not.
yeah, for this one is we're using hat map or hat scan for in the training and
Mhm.
but in deployment, you can do it either way, you can do like fixed stare, you can do
Mm-hmm.
like just based on LiDAR, right? But we ended up, I think there's some problem with the LiDAR setup. We just ended up with some pseudo, you know,
Mm-hmm.
perception framework. So it's not like
Yeah.
fully. You can see like all the OptiTrack markers in the in here
Yeah.
actually.
Yeah. Yeah.
OptiTrack markers. Yeah.
Yeah. Okay. Yeah. Yeah. We're trying to get some of this visual, autonomous, MPC planner using diffusion approach and then, looping. Yeah. It's still kind of hierarchical setup. But we feel that have more potentials, in terms of
Yeah.
online
Yeah.
planning.
Sounds very promising.
Yeah.
Yeah.
Yeah. Yeah. Cool. All right. I think we are already running out of time. Any last minute questions?
I actually have a quick question about perception, like how perception plays a role. Basically, like you have a reduced order model, and then you basically already like kind of like know the terrains ahead of you, and then you generate just like cinematic motion, cinematic trajectory, and also footstep
Mhm.
um motion as well, footstep placements as well. So like in the training, I use also like use the perception as part of the input to the network, or just blindly like following this like cinematic like generated by the lib model.
Yeah, so the terrain information or the sensor input is part of actually part of the training. So you can see this is a high scan that the robot will be able to see inside of the training, and how this would be used is similarly how we gonna set up our LiDAR for the actual deployment. Yeah, so it is based on the high scan, but however you want to get the high scan in deployment is up to you, right? You can do cameras, lidars, and just some fixed method, right? Or yeah,
So in the deployment, you don't have this like head scan. You only it's basically like teacher policy have the head scan, but like
yeah.
maybe like student policy don't have that.
No, student policy does have it.
But like in deployment, uh, like you
Yeah,
don't
in
you don't have
deployment
that.
we will still have it. Yes.
Uh,
Yeah.
Okay, all right. I guess we can wrap up this seminar and yeah, thanks again, Junheng, for this wonderful talk.
Thank you for the invitation.
Yeah, yeah, we look forward to more work, from you from your lab and let's find some way to collaborate.
Yeah,
Maybe.
absolutely. Yes, yes. Let's talk more. Yeah, I really like what you guys doing here. Yeah.
Cool. All right. Thanks, guys. All right.
Okay.
Bye.
Thank you guys.
Yeah.
See you.